Okay, good afternoon, everybody. I hope everyone's having a wonderful day. So before we get started, I just want to point out the final assignment is out. It came out later on in the afternoon on Monday. It's due by the end of December 3rd. It is not as long as the previous assignment, but it will require you to make some careful thinking on things. So for example, I gave you a couple of different Turing machine-based variants, and I asked you to prove their equivalencies with the Turing machine as we've defined it. So in these, you'll be probably having to prove two directions of an equivalency proof. So meaning that you'll have to start off with some Turing machine, and your job is to show me that you can simulate the other Turing machine using yours, and vice versa. So if I start with the variant, I got to see how you simulate the original Turing machine, and vice versa. So keep in mind when you're doing this, it don't necessarily have to be restricted down to, oh, it has to follow an exact set of moves. You also may have to describe states that you're going to have to add. So you think of it like a construction, just like what we've been actually doing today and what we did last class, where I usually describe some construction to you. So your job is just to tell me what that Turing machine will look like as your model, and vice versa. So that's the first problem. The second problem, I get you to encode for me a binary string for a Turing machine that I've described to you as a transition diagram. So then the last problem is just getting you to try out doing a couple of these reductions. And that's the final assignment. So hopefully have a good time with it. And I must stress this, that it will take some time to think about some of the ideas. So just don't wait till the last minute, even when I tell you, oh yeah, it's not that long of an assignment. So just take your time with it. I recommend heck, if you want to do something a little fast, do the second problem. The second problem doesn't take very long. And then work on 1 and 3. But yeah, this assignment is very proof heavy, so you will be spending some time proving some things. So anyways, take a look at that when you get a chance, and feel free to ask me any questions about it, either at office hours, or email, or before class or after class. I'm very happy to answer these things. I mostly just because today I want to get back to where we were, and some parts of this are going to be relevant and helpful for the assignment, okay? So, are we all ready to go? Give me a thumbs up if we're all good to go. Okay, great. Wonderful, wonderful. So, I thought we would do another example of doing one of these reductions. So just remember, when I give you a reduction, my job is to say, okay, if I give you two problems or two languages, my goal is I want to take and perform some reduction from one to the other. What I want to do is I want to map all of the instances of one into the description of the other. So I take one of these, I want to make it look like one of those. And then my job is to, under the presumption that I know something about the undecidability of this one, that I want to be able to say something about the second language or problem. So we're going to use that same strategy here. So I'm going to consider the problem of deciding whether an arbitrary Turing machine accepts for no strings. That means the language of the machine M is empty. Now, it shouldn't be confused with the fact that, yes, you can design a Turing machine that does, in fact, accept the empty, like it has an empty language. Remember, we actually described such a Turing machine some while back when we were encoding Turing machines. I gave you that Turing machine that just doesn't really accept anything. That's essentially what I'm saying, is that we're given an arbitrary Turing machine, and your job is to tell me if its language is empty or not. In this case, to be in this language, it means that the Turing machine's language is empty. So, what I want to do is I want to prove by a reduction that the following is the case. So here's the theorem. So I'm going to show that this LE is undecidable. So I'm going to prove this for you. So I must stress that there's a couple of different ways of approaching this when you have a reduction in play. One is you present the reduction, but you prove it via contradiction that this language is undecidable. The other one is that you can actually use the reduction directly to imply that it's undecidable. So I'm going to show you an example where I'm going to use the contradiction like I did last day. The next example I'm going to do is just going to be where I'm going to just assert, based on the properties of undecidability over a reduction, that the consequent language I'm interested in is in fact also undecidable, okay? So I'm going to set this up as a contradiction proof. Assume there is a decider. So assume there is a decider for E. We'll say decider E. I want to be a bit careful about this. A decider E. So that my LE language is equal to the language of decider E. So first I'm going to present the reduction to you that I would like to use. So I'm going to use the universal language once more. First, we present the reduction from the universal language to LE. So I'm saying that I'm going to be performing a reduction from the universal language to LE. And now I'm going to describe this reduction to you. Now, this is going to be a little strange, but I'm going to point this out because this is a very common pitfall when learning about these types of languages. Do you see anything that's a little different about this description for my language? Does anybody see anything that's a little different than our previous examples? Think back. Yeah, it's just the description of this is just a machine. Notice it doesn't have an input with it. So we have to be very careful about this. So you got to think about this now as, okay, this is the description of just a machine. And to belong to this set or language, it means that there has to exist some input for M such that, so if I were to look at any one of the inputs for my description, it's always going to simply reject, right? That's what it means to be in this. So I have the empty language, right? So just keep in mind that when I talk about this description of a machine M, remember, I can talk about the description of M with respect to the input that M receives. So just be very careful about the way, so just when I describe this to you, just keep that in mind, that I'm going to be constructing some machine that's going to be of the form for LE, okay? And notice that it doesn't have a W here. So the reduction, I'm going to call it F because it keeps things nice and flowy with the things I'm doing. Now remember, I'm going to take the universal language and then I'm going to reduce to this LE. Now, what does that really mean? What's my strategy? I would like to be able to show you how I can design a decider for the universal language. That's going to be my end goal here. So I'm going to have F. It's going to take in the input for, this would be what's going to be in relation to the universal language. And it's going to give me some encoding of a Turing machine, M prime. Is given by a modified Turing machine, M prime, which in its description, so this is me describing the construction to you. In its description, for a given input X. So remember, when I have this Turing machine's description, remember the Turing machine will interpret some input and I'm calling it X. So usually I call it W, I'm calling it X here, okay? So just be very careful when you're thinking about this. Now, there's one thing that you need to notice about this reduction that I'm going to do based on how I've defined it here. So when I do this, I have access to W, right? And that's the W that's related to my universal language, right? So when I'm doing this construction from the perspective of describing this Turing machine, so when I'm provided M and W from the perspective of M prime, when I describe this to you, is W fixed? Well, think about it. Think about it. So remember, keep in mind, I'm just talking from the perspective of constructing M prime. Indeed, you can get different M's and W's, but think about it when I get to the stage where I'm given these two. I can use M and I can use W, right? So when we build this Turing machine, we're going to bake right into it like a cake. I'm going to bake W right into the description of the Turing machine. So that's what I mean by fixed. So I can just simply, when I'm building this, I can take W as a part of the description of my Turing machine that I'm going to build, because I'm given M and W. So just watch carefully what I'm going to do here. So if X is not equal to W, we're going to reject. Now, if you're wondering how you would achieve this step, all you're going to do is you're going to add some more states to M prime so that you are able to perform the zigzag process. So you just augment M so that it has the ability to do the zigzag comparison to see that X is not equal to W or X is equal to W. Now, you might ask, Dan, why are we doing this? You're going to see in a moment. So for now, just let's proceed. Otherwise, X is going to be equal to W. And now we're going to run M on input W and accept if M accepts. That means, of course, if M rejects, then you're going to reject. So you might ask, Dan, why would I do this? Like, this seems really weird. Like, now you got to look at it more from the perspective of when I was drawing those boxes. So let me just kind of do a mini version of this. So if I have, remember, I get in for my reduction. I get M and W, right? So what I would like it to do is it's going to leave on the tape M prime. So a description for a Turing machine M prime. And that's going to be fed to my decider. This is going to be the decider E that I have right here. So what I'm going to do now, so remember, this is what F is. So we got to remember, when I cook up M prime, what I would like E to do, remember E's job is, at the end of the day, there's going to be something that comes out of here. It's either going to be accept or reject. Now, I can do all sorts of stuff inside this box. Just remember that. So my job is right now to show you that by the sake of contradiction, so I'm going to try to use contradiction here to show you that using E, I can actually decide the universal language. So whatever's in this box, as long as this exists, I can decide the universal language. But remember, the whole idea here is that I know that the universal language doesn't have a decider, right? So that's how we're going to get this contradiction. So think about it. What I want to do is I want to bake into, I like to think of it like a cake. So I'm going to bake into my M prime that if X is not equal to W, you're going to reject. Now you might ask, why am I doing that? Now, I would like to only consider when M prime, so I'm going to build M prime so that when M prime gets that input, what I'm going to do is I'm going to effectively ignore the input if it's not equal to W. Because really the question, remember, in the universal language, what is my goal in the universal language? Can somebody tell me? What's the universal language again? Can somebody tell me? Yeah, so it takes the string, it's going to be that coding of the machine in the string, and you want to know if it accepts it, right? Yeah, exactly. So now what I would like this to do is basically do that for me. So if I can make it so that the input description, remember, I'm baking W right into the description of this machine. So if it's getting W right here, remember, there's W right here. So I'm effectively just trying to make it so it passes through so that when E gets this, it has to effectively run M on W. Does everybody see that? So I'm going to try to make it so that E is forced, because E is a decider for LE. I want to force it to effectively run M, okay? That's really what I would like it to do. So I'm essentially playing around with the Turing machine's description so that it's going to effectively require it to solve our problem over here, deciding the universal language. That's going to be the trick. So here's the observation I want you to notice here. So that's the end of this reduction, believe it or not. So notice that for M prime, either the language of M prime is going to be equal to W. So it's going to be the set containing just the string W. Or the language of M prime is going to be empty. Does everybody see that? So notice that, remember, just look at what the reduction does. So it only runs, it only accepts, right? The only time it ever accepts is when X is equal to W. So the input would be W. And this is the only circumstance for which the machine could accept, right? So there's really two possibilities that can happen with M prime. Either X is equal to W, and it means M on input W accepts, right? Or it rejects, so meaning either the first case happens or it rejects right here in this step. We really care about this part right here. So does everybody sort of see the trick I'm using here? I'm baking right into the description of the Turing machine, effectively the test to determine if W is going to get accepted here. So it's a little crafty, if I might say. So are we okay with this so far? So I'm going to now describe to you how I'm going to make a decider for the universal language. So here we go. So now I'm just going to describe that box to you, the big box. So notice that for M prime, either, we don't want that. I'm getting one step behind myself. I wrote it down there. My apologies. I need to describe the decider I would like to use here. So now given input MW, we describe the algorithm U. Now, you might ask why I'm using the word algorithm, because I colloquially have been using the word algorithm again as a decider, right? It's also to make things a little less confusing for you, so that you have this thing where, okay, there's a reduction, there's some Turing machines, and then we're using those Turing machines in my big box. So I want to describe it as something a little bit less confusing. So I'm going to call it U like I did last time. You don't have to call it that. That's just what I've decided to call it. Describe the algorithm U so that the language of U is in fact the universal language. So here's the idea. So here's the steps in my algorithm. I'm just going to apply the reduction. So we're going to apply given M and W. We're going to get that Turing machine M prime as described to build M prime. Then you're going to run the decider. You're going to run decider E. Remember, that was what we would like to do on input M prime. So you're going to run that decider. Remember, I've presumed that this decider exists. And now I have two possibilities of what I would like to do here. So if E accepts, we're going to do something. Otherwise, sorry, lowercase o, otherwise, if E rejects, you're going to do something else. Now, the reason why I'm using this contradiction-based proof setup is that in the purest sense of a reduction, you usually like it so that the yes answers match up with the yes answers and the no answers match with the no answers. This makes it a little easier for me to work and wiggle things around because I can presume the existence of a decider, and then my goal is just to describe a decider to you for the universal language. So I don't have to work within those restricted constraints if I want to use a more classical interpretation of a reduction. So just remember that from the other day. Remember my picture? I had the yeses and they go to the other language and their yes instances there, and no for the no. So I've deliberately designed the proof this way so that I don't have to worry about that purity. So I have a question for you. What should E do if it accepts? Based on what I just said. I gave you a bit of a hint. Yeah, you're going to reject. Yeah, you just reject. Because remember, if you're going to reject here. So you're going to reject, and what do I do in the other possibility? You're going to accept. Perfect. Now I'm going to explain why. So that's wonderful. Bang on, perfect stuff. So now I'm going to write out my reasoning here. So if E accepts, notice that this happens only when the language of M prime is empty. Which only occurs when M does not accept W. So that's the first possibility. So that's why I'm okay when E accepts like this, I reject. So we have to be very careful about this. This is because of the way I crafted M prime, right? Remember, there's only two possibilities that can happen with the language of M prime. Either it's going to have a set with just W in it, or it's going to be empty. Remember, when I feed this over to this decider over here, and it says, okay, I'm going to take in that description of that Turing machine, and it takes input X, but remember, I just made X into, when I see X, and it's not equal to, if it's equal to W, I'm going to simulate M on W, right? So if it accepts there, that means it had, in fact, had a W, right? So that means that, okay, well, like that means it accepts that W that's in that language originally, right? But you know that just simply means it's not empty, right? So now the other possibility is otherwise E rejects. So it must be sorry, I had the reasoning backwards here. My apologies. What I'm writing here is correct. I was getting ahead of myself. This is the part I'm referring to when I said, like I said, we flipped the reasoning here. Must be that M prime equals W. Actually, I think I did state it correctly. I just get a little ahead of myself sometimes. It's equal to W. And as a consequence, M accepts W. So it's a rather crafty little trick that we're using here. So what does this mean? Hence, the above algorithm decides the universal language but the universal language is undecidable, which of course is a contradiction. So I'll just mention that in parentheses, a contradiction. You don't have to write that down. It should be apparent to the reader. And if you want to add in the one bit of line of reasoning, you can always say, therefore, since the universal language is undecidable, our language LE also must be undecidable. So, are there any questions about this proof? So this one's a little trickier because now we had different inputs for our two languages, right? So all I did, the big trick here was that I baked in like a cake. So I'm given my ingredients, and what I do is I take W and I shove it into the cake and I throw it in the oven to bake it. That's basically what I did. It's quite a graphic but delicious sounding idea. So I have a question for you. Is it okay if I move on over here? So give me a thumbs up if we're all good to go. If it doesn't click right away, just give it some thought. It's a little tricky, this one. So if we're okay with this, let me proceed over here. I have a question for you. So let me just erase this. So we talked about LE. And we generally like to also ask questions also about if a language is not recursively enumerable, right? Sometimes we like to know about that. But remember the other lecture, I think it was a couple lectures ago, I talked about properties that when we talked about recursive languages, I talked about how there's relationships between the complement of a language versus the language itself if they're both recursively enumerable. Right? Do you remember that? I talked about how if they're both the language and itself are recursively enumerable when I take L as its complement, that means that the original language also has to be recursive, right? So I'm going to use a little bit of line of reasoning here to ask you a similar kind of question. So is LE recursively enumerable? So here's the thing I want to point out to you. So I'm just going to note this down. I'm going to say it can be shown. It can be shown. It can be shown that the problem of deciding if a language as in LE, so is not empty. So this is essentially the exact same definition I gave you for LE, except replace the equals empty set with not equals empty set. Is not empty is recursively enumerable. Now, if you're wondering about the details about this, you can check out chapter 9.3.2 of the Hopcroft book of HMU. If you're wondering how this exactly works, there's more details there. And in fact, if you want to show that this language I've just described to you, this one where you're checking if the language of the machine is not empty, the reduction that you actually use there is nearly identical to the one I presented over there. You just don't flip the logic. And that's why I used the setup I did. So let's see. So I have a question for you. If I told you that determining if I give you a description of a Turing machine and I ask you, does that machine, like, is its language empty? But here I'm changing the equals to empty to not empty, and I'm telling you it's recursively enumerable. And I've already told you that LE is undecidable. What can you infer about LE? Is it recursively enumerable? Any ideas? It's not exactly. If it was, in fact, the way you can prove this, I give some more details about this in the notes, but if you do this, you can just use contradiction. Just assume that both LE and this language were, in fact, recursively enumerable. And then you just point your finger and say, okay, well, it says this one, this language here, it is recursively enumerable. So if it was the case that LE was also recursively enumerable, that would also imply LE is recursive, right? But that means it's decidable. Which is, you're going to get a contradiction because I just proved over there that it's, like, you can't have both ways, right? In fact, you could also show that this language that I've just also described to you is also undecidable. And like I said, you use a reduction very similar to the one I described in our previous proof. So if you're wondering about that, just take a look at the details there. The construction they use is very similar. Okay, so let me just, so this is saying, implying that LE is not recursively enumerable. So just to clarify, because I'll write out the details here. So I say this is because if both this language, the one I just described above, if both this language and LE were recursively enumerable, it would imply what? Based on the theorem I gave you a couple lectures ago. It would imply both are recursive. And the thing is, neither of these are true, right? So hopefully that clarifies that. So you can oftentimes use the properties I've talked about previously to infer things about if a language is recursively enumerable or not. So is that kind of neat? So now I've given you some undecidable problems, right? So now you have some pool of problems you can play around with. I'm going to do one more example. This time I'm going to use the reduction directly and use the property I showed you last day about the connection between two problems when I give you a reduction. So I'm going to consider another language. So here's another example. I'm going to consider the following language. And you're going to first ask, Dan, why does this language matter? And this is the main reason why I want to show you this one. So suppose I have an encoding of two Turing machines. M1 and M2 are Turing machines. And the language of the first Turing machine is equal to the language of the second Turing machine. So I'm going to consider this one. And I want you to think about what this definition means for this language. Think about it in the most practical context you can think of. So think about this in connection with something like the Church-Turing thesis. What can you infer about if I was able to have one of these right here? If I was to tell you that, if I had something like this, what would it imply? Can somebody tell me? So remember, I have two descriptions of machines, and I want to know, so these are two arbitrary Turing machines, and I want to know if they're equal in terms of their languages they recognize. Think about it in the most practical sense you can think of. So if there aren't any suggestions, here's essentially why you should care about this language. So this is one idea. There's many other implications you can make. But here's one. So suppose those two Turing machines had corresponding computer programs. And I want to know if your one computer program outputs the same things as my other computer program. And say somebody comes along and says, okay, my computer program has 10 million lines of code. And your other program has, say, 1,000 lines of code. Wouldn't it be nice if I was able to tell you that the one program always has the same output as the other Turing machine or other computer program? That would be an absolutely killer application, right? Like that would be amazing, right? Does everybody see that? So yeah, so all I'm saying is that this would have absolutely killer applications in industry, right? Like I could just straight up tell you, oh yeah. Here's your computer program, here's mine, and I could tell you that for every single input of your program, it produces the same output as mine, which is that's actually quite incredible, right? That's what this language is representing. Does everybody see that? So this is why I'm presenting this one specifically to you, because I could have presented many of them, but this one I think is rather important. Now, this is me being reverse Santa Claus, okay? So here's me saying that this is also undecidable. So LEQ is undecidable. And now I'm going to pick up one of the problems I've already used today. I'm going to take LE and I'm going to use LE in my reduction. So I'm going to use the reduction directly and impose the properties of undecidability from LE onto LEQ. Because remember, if I give you a reduction that looks like this, like say if I have LE and I perform a reduction to LEQ. If I know LE is undecidable, what does that mean for LEQ? It's undecidable as well. So all I have to do, logically speaking, is just present this reduction to you and just impose that property. So let's go over to the other board and let's prove that, okay? Now, while I'm erasing the board, I want you to think about in your head, think about those boxes that I was drawing. And think about, okay, well, what if I gave you like two arbitrary Turing machines? And I was like, okay, well, what can I craft like a really nasty looking one that would really like cause me to decide effectively that language over there, that LE one. So that's usually the intuition you want to think about when you're designing the reduction. So here's the proof. So I'm going to do this via reduction. I'm not going to use contradiction at all. I'm just going to directly prove it via the reduction. So we use a reduction. So we're going to use from LE. So we're going to reduce to LEQ from LE here. So I'm going to consider the reduction. Consider the reduction. A reduction F from LE to LEQ, where, now I like to usually write it out just so it's clear what we're talking about. So I'm going to say F is going to take a description of a machine, and I'm going to give a description of two Turing machines. One I'm going to call M prime, the other one I'm going to call N. So here we go. So keep in mind, remember, the whole idea here is I'm going to try to make it so that I can get it so that this language, the LEQ one, does all the work for me. I want to think about it as helping me decide LE. So the reduction uses M prime is going to be equal to M. So M and M prime are going to be the exact same. And I'll say where, let's go where, Turing machine N is so that on any input, it halts and rejects. So that the language of N is empty. Does everybody see the trick I just did here? Isn't this is rather slick, what I just did here. Does everybody see what I did? So remember, what I'm going to effectively do is make one of the Turing machines, in this case N, I'm going to make that one be a Turing machine that only accepts the empty language. So its language is the empty language. So because I always craft it so that on any input it halts and rejects. So that means that now what it's asking, if you think about M prime and N, it's given M, because remember M prime is equal to M. And I'm asking, is the language of machine M in fact equal to the language of N, which is in fact equal to the empty set, or empty language? Does everybody see what I just did there? It's that kind of crafty. It's very slick and simple. So now if I can get the LEQ to do that for me, then I'm done, right? But I just presented the reduction for you. So I just got to verify that this is in fact going to be the case. So let's make an observation. Whoops, that's a little squeaky there. Observe as a consequence of our construction, because this is all entirely based on the construction. So sometimes it's really helpful to say this. As a consequence of our construction, since the description of, so if I give you M, I tell you that it's in LE, if and only if L of M is equal to the empty set, or empty language, it is that the language of M is equal to the language of N if and only if M and N, keep in mind, remember, M is equal to M prime, so I'm just going to write M here, is in the language of LEQ. So this is the big observation, and that's what I was pointing at when I was talking about this earlier. So now all I'm going to do now is I just need to invoke the property I know about LE. As LE is not recursively enumerable. In fact, I could even make that statement even stronger, right? I could say that LEQ is not recursively enumerable, right? Let me just make that small tweak on my side. So if you have your notes in front of you, you can always say and is not recursively enumerable. Remember, I can inherit that because of the reduction. So I could have made I would argue, a weaker statement and said, oh, okay, it's just undecidable. Here's a much stronger statement. As LE is not recursively enumerable, LEQ must also be not recursively enumerable. And we're done. That's it. Believe it or not. Okay. So you can always reformulate this proof, by the way, in the manner that I did actually earlier. So remember when I used contradiction? I can formulate the same proof using contradiction as well. So I want to spend the last few minutes here just talking about a couple of other interesting results I want you to be aware of, and just the fact that every time I've done this, I've always had one reduction, right? But implicitly, there's actually a chain of reductions that are in play, right? So for example, when I considered LU, right? And so for example, when I did a reduction, I had it where like LU reduces to LE and it reduces to LEQ. Notice this is a whole chain of reductions that are happening here, right? So you can actually chain together a whole bunch of reductions to get you to an actual much more broader statement. So let me talk a little bit about that. I'm going to make two remarks, then we're going to end things off for today. So I got to state an important theorem for you. I'm not going to prove it for you, but actually, believe it or not, it uses a strategy. It's very similar to one of the proofs I showed you today. But let me describe one result for you, because I promised you at some point I was going to tell you how it's possible and how it's done. So I'm going to say sometimes reductions can be quite complex. For example, to prove the undecidability of determining if a context-free grammar is ambiguous, we do the following reduction actually in this proof. So remember I told you that there is no algorithm that can tell you if an arbitrary context-free grammar is ambiguous or not? Remember I told you this some while back? I want to show you the reduction that you can use to prove this. So I'm just going to give you the overview of this proof. So first you start off with the universal language. And then what you do is you use a problem, it's called the modified post-correspondence problem. If I had another week in this course, I would show you this problem. But if you want more details about this, you can look at chapter 9 of the Hopcroft book. They go into, and also I think Sipser also talks about post-correspondence as well. So there's this problem called the modified post, so it's posts, this is a name, posts correspondence problem. I like to think about it like a game of dominoes, but there's a lot of different ways you could think about it. So I'll abbreviate this as modified PCP. So post-correspondence problem is PCP here. You can reduce this to PCP. And then what you do is you reduce this to the ambiguity of context-free grammars. So when you work your way up to some of these more broader classes of problems like this, they could get quite intricate, the reductions. And the whole idea and the rationale based on the same kind of argument I used over there is this is undecidable, so this is undecidable, right? That means that this is also undecidable, hence this is also undecidable. That's the power of a reduction. Is that interesting? So let me just summarize one other theorem I want you to be aware of. So I'm going to describe one small thing as something I'm going to call a property. A property, so that's just something else. A property, so this is just some jargon I'm using. A property is a set, which people would call a class of recursively enumerable languages. So it means it's just some language that there exists a Turing machine that will recognize that language. A property P remember, this is a class of recursively enumerable languages, is trivial, this is a technical term, is trivial if the class is empty. If the class is empty, or the class of all recursively enumerable languages. So we're interested in these so-called properties, and we're going to be interested in the ones we're going to call non-trivial. So we are interested in the non-trivial properties. So that's everything that isn't trivial, by the way. So you often will get languages that look something like this. So all the ones we've seen today pretty much are like this. In particular, the empty one that we've seen at first. So given a Turing machine, M, is the language of M in the property. So for example, P can be, is it that the language M is empty? That's an example of actually one of these properties. And that's actually just our first example I gave you. So there's many things that can be P. I'm going to give you examples after I state the theorem. So, and you might ask why? It's because if you're asking about P in this case, it's simply this set. So this is in fact a recursively enumerable language because there exists a Turing machine that can recognize the empty set or empty language. So it's some Turing machine. Just be aware of that fact. So here's the theorem. So I apologize for going a little longer here because I want to make sure I state this because this is a really important result. So it's called Rice's theorem. So this is from the mid-50s if my memory serves me correctly. So this is Rice's theorem. So think of it, the way it's spelled is just like rice, the food. Rice's theorem, but it's not named after the food, just to be clear. Rice's theorem, it states that every non-trivial property of the recursively enumerable languages is undecidable. Is undecidable. So you might ask, Dan, okay, what does this mean? So I want to give you just a quick, it's okay if I take one more minute. I'm going to list you 5 very important examples that you could get as a consequence of this, just to give you an idea of what kind of things this means. So the example I showed you earlier, the very first one is actually, you can also invoke Rice's theorem to get that one. All you do is you just tell me what this is. So this is another technique you can use to show undecidability, but let me just quickly list just a few examples here, just to give you an idea of how broad this theorem is. Because essentially this theorem tells you that any interesting semantic property of a language is undecidable. That's what it's essentially saying. So I'll just mention that. In plain language, this is just me being plain and layman with you. It states that every interesting semantic property So just when I say that, I'm talking about the language itself. Notice the way I define what a property is and the way I formulated that question to you involved the description of the language, not the Turing machine. But you can describe different things about Turing machines with languages, just to be clear. There can be Turing machines that are undecidable, but languages that involve Turing machines that are undecidable, but this involves the languages themselves, just to be very clear. Every interesting semantic property, property or question about the language accepted by a Turing machine is undecidable. So a lot of the questions we talked about today all involve things like, oh, is it empty? If I give you two Turing machines, are the languages equal? These are all rather what you would call interest of semantic interest for when we talk about Turing machines and what we would like them to do. For example, you can think about them in a very utilitarian way and think, okay, I just want some program that checks if two programs or their descriptions, actually based on their descriptions, can tell me if they actually output the exact same things. So very much properties like this all fall under Rice's theorem. That's what I'm saying to you. So it's like a giant minefield of undecidability results. So here's some examples. I apologize for going longer here. So here's some interesting consequences. So you could say that deciding whether L of M is regular. So if I give you a Turing machine and I ask, is the language of that machine regular? This is undecidable. Strange as it sounds, because with a DFA, it's most certainly decidable, right? But not with a Turing machine. No, Turing machine's way too broad. You could do the same thing. Is context-free? Is undecidable. You could also ask even if it's not regular. You could also ask all sorts of other fundamental things, whether, for example, if it is finite. So if you want to know if L of M is finite, is undecidable. You could also ask if it's infinite, is undecidable. So I'm hoping I'm hammering in the idea that there's a lot of things that Turing machines can't do with an arbitrary Turing machine. It's just a giant trap of things. In fact, you could even do something very simple like this. So deciding if L of M contains at least two strings is undecidable. So if you wanted to know, for example, you're given an arbitrary Turing machine and you want to know its language contains at least two strings, that's also undecidable. All sorts of things like this. If you want to ask for a certain pattern in the string, like you want to guarantee it's always going to have a certain thing. Like on the assignment, I ask, okay, is it empty? Like instead of it being like, okay, is it the empty language? Is it empty? If it does it only accept the empty string. Like these are all things that fall under Rice's theorem. That's why I'm saying it's really damning. It's the worst kind of reverse Santa Claus I can give you among a lot of these. But the point here is very simple, that there's a lot of different ways you can show undecidability results. And I'm hoping I gave you a good flavor for different kinds of things that we cannot do with computers under the assumption that the Church-Turing thesis holds. Okay, so I apologize again for going longer here today. I'll try to make up for it next day, okay, everybody? So I want to say thank you very much, everybody, and have yourself a beautiful day. I'll see you later. I can always stick around a little longer after, but